Hello students, welcome to this course on Introduction to Hydrodynamic Stability. Uh, this is the course number CHE 614 of IIT Kanpur. My name is V. Shankar from the Department of Chemical Engineering, IIT Kanpur. So this course is CHE 614. And the mode of delivery of this course for this semester will be through online videos. The videos will be uploaded in the MOOCit portal of IIT Kanpur. We will upload roughly around 3 videos per week. And there will also be a approximately 1 hour Zoom discussion hour every Wednesday, and this will be from 12 to 1 p.m. each Wednesday. The announcements for the course will be made through the announcements tab of the course portal. So you should keep watching. The same announcements will also be sent to the course alias CHE 614A at the rate of iitk.ac.in. Okay, so all the registered students are part of this mailing list, including the instructor, that is myself, and so we will be able to correspond to each other through this. Now, there is another unofficial email ID for the course, that is che614a.iitk@gmail.com. Now, this is the course alias that I will send to emails to you. Okay. Now, this is the course. This is the informal email address wherein you will send emails to me. Now, this can be regarding some issues with respect to uploading of assignments or exam solutions through the online portal. So you will use this email address in case you are not able to upload or there are some issues with net connectivity and so on. Right. So this is the email address wherein you should submit anything that is related to the course. You should not send it to my personal email address. You should send it only through to this, and we will keep checking this, and then we will provide you any feedback or address your queries. Okay. Now, this is the email address that is officially created by the institute. So this is used to send any announcements regarding the course. So that is automatically synced with the portal, the MOOCit portal. So you will be able to receive whatever announcement that I post. I will be able to send an email through the course alias as well. Okay, and so the course will have the first course handout has already been posted in the portal. Please take a look at the PDF has been posted in the portal. Please take a look at that in detail regarding the course objectives, the grading policy, and other administrative details regarding the course. So this is something that I won't repeat here in the interest of time. Now, there is one thing that I would like to stress on though, which is the course textbook. I will follow two introductory textbooks. That one is by Philip Drazin, and the title of the book is Introduction to Hydrodynamic Stability. The other book is by Francois Charroux. This is called Hydrodynamic Instabilities. I will of course not strictly follow these textbooks, although most of the topics I'm going to cover are present here. I will of course use explanations from variety of sources and from my own experience. Here are some reference textbooks which are at a slightly advanced level. The first is by the same Drazin and Reed. This is a classic in this area of hydrodynamic stability. This is simply called hydrodynamic stability. And the second book is by Peter Schmidt and Dan Henningsen. This is called Stability and Transition in Shear Flows. Okay. The third is a very old classic by Subramaniam Chandrasekhar. This is called Hydrodynamic and Hydromagnetic Instabilities. And the fourth is a textbook that contains numerical methods. This is called Spectral Methods. Okay, now having said that, we will primarily follow the first two textbooks. There are reference books are just for those who want to delve more deeper into the subject. Alright, so now let me in this module, what I'm going to do is to give you a brief introduction to the subject itself. The subject of hydrodynamic stability is a sub-branch of the broader subject of fluid mechanics or fluid dynamics, and the subject of hydrodynamic stability is concerned with the two drastically different flow states. Okay, what are these two different flow states that we are interested in? One is of course called the laminar flow, which you may be familiar from your earlier undergraduate courses. The other is called the turbulent flow. Okay, now the subject of hydrodynamic stability talks about the transition between these two flow states. How does this transition happen? Okay, that is one of the main motivation of hydrodynamic stability. Just to refresh your memory, laminar flows are flows that are typically observed at slow speeds or slow flow velocities, and they are typically very relatively simple in their kinematics, in that the flow field is not very complex. I'll give you some examples as we go along. And again, the time dependence of the flow is not there. That is, the flow can be steady or not complex enough. Okay, the flow can be unsteady, but the time dependence is not very complicated. Okay, so this is these are the characteristic features of laminar flow. Now let me show some examples of laminar flows that you must have seen in your earlier courses. So for example, if you take two parallel plates and then move the top plate related to the bottom, then you get a velocity profile like this, a linear velocity profile, and this is called the plane couette flow. Okay, now this profile, here I am plotting the velocity as a function of the vertical distance. This is x, this is y. There is only x velocity that is non-zero, and it is steady in the sense that it is independent of time. at a given position, right? And the top plate is, let's say, moving with a velocity v. Now this is the plane coed flow, which is an example of sorry about this, a laminar flow. You have what is called flow in a pipe. Okay, let me draw a pipe, a circular pipe of circular cross section. Okay, now here one has a parabolic velocity profile. This is called the pipe Poiseuille flow, or sometimes referred to as the Hagen Poiseuille flow. Here again, here because it's a cylindrical pipe, one has to use a cylindrical coordinate system. This is the axis Z, this is the radial coordinate R, and theta is going around, okay, like this. So here the only non-zero velocity is Vz, that is non-zero, and of course it is steady. This is another example of laminar flow that you might have seen. Now the same Poiseuille flow can also happen between two, in a rectangular slot. Instead of a circular pipe, you can have a rectangular channel, okay, like this, and there is flow here in this direction. This is the x direction, let's call this the y direction, and into the slide is the z direction. Now if this width is very large compared to this height, if w is large compared to h, then the flow becomes effectively two-dimensional, in the sense that the side walls, these are the two side walls, these are so far apart that you can treat the flow to be just two-dimensional in the x y plane. So here is x, here is y. Again you have a Poiseuille parabolic Poiseuille velocity profile. Sorry about this caricature, let me draw it properly. Okay, this is supposed to be a parabola. This is called the plane Poiseuille flow. Okay, this is again an example of a laminar flow. Another example of a laminar flow is a flow between two circular cylinders with two concentric circular cylinders, with one of the cylinders moving with some angular velocity omega. Here if you look at it from the top angle, the streamlines in the simplest flow will be purely in the azimuthal direction, and this is another example of a simple laminar flow. This is called the Taylor coed flow. There are many other examples, but I'm just trying to tell you a little bit about laminar flows that you might have seen already in your earlier courses. Now as opposed to this, suppose before I go to turbulent flows, in any of these geometries, suppose I pick a point in space and then ask the question, what is the velocity as a function of time? This is called the Eulerian velocity, right? Because you're fixing the location, spatial location, and you're just measuring the velocity as a function of time. You'll find that the velocity remains constant, okay, if the flow is steady. Okay, this is steady flow. Instead of steady flow, suppose you ask the question that you're going to start the flow from rest. This is called the startup flow, and then you suddenly start one of the boundaries, or suddenly you switch on the pressure gradient. You will typically find that even in this case that the flow is unsteady by definition. So at a fixed location in space, the velocity will initially increase and then eventually it will approach the constant value. So even though this is time dependent, the time dependence is relatively simple. Okay, this is what so the flow is laminar. So laminar flows are characterized by relatively simple time dependence, like the one I showed. Now if you look at turbulent flows, in contrast, they are inherently unsteady. Okay, you have the flow is three-dimensional and the flow is chaotic or random without any pattern. What I mean by this is the following. Suppose you have a flow in a pipe. Suppose the flow is turbulent. You're still applying a constant pressure drop. The pressure drop is independent of time. Okay, there is no the forcing or the driving that is used to drive the flow is independent of time. Yet the outcome, which is the turbulent flow, is time dependent. And it is time dependent in a very complicated way. So this is very peculiar. You are trying to drive the flow with a time independent driving, that is the pressure drop, but yet the output is very complex and it is time dependent. If I plot the output as a function of time, okay, and let me just explain what this symbol is. Suppose I plot the output as a function of time, what I'll get something is like this. Okay, I'll get a very suppose this is the velocity as a function of time, time in the x-axis. So there is an average velocity or the mean velocity which is in the flow direction, let's say, but about that non-zero average there are a lot of fluctuations, very significant fluctuations, and which are chaotic in the following sense. If I were to repeat the experiment and measure the velocity at a given point, the answer I'll get is will be completely different from the earlier experiment. So that is what I mean by random fluctuations. Okay, so the turbulent velocity field is highly fluctuating in the sense that if you repeat the experiment, there is no guarantee that you will get the same signal. You will get you will indeed get a completely different signal. Now, this is not the only example of a flow transition, although this is one of the most important examples of flow transitions. There are other examples of a change in the flow state. And for example, if you have opened a tap in your kitchen or bathroom, and if you open the tap very gently so that you are not opening it fully, you just open a little bit, you will find that from the outlet of the tap you will find a thin liquid thread that comes down. Okay, I'm going to exaggerate this for the sake of illustration. So this is an example of a cylindrical liquid jet. Of course, the jet is flowing, it's continuously, liquid is coming out of the tap, water is coming out of the tap. Now what you will have, if you look at it carefully, what you will observe is that eventually the cylindrical jet will become, the shape of the cylindrical jet will become different, and this will break down into drops of water. Of the jet into drops of water. Now this is called the Rayleigh or capillary instability. Okay, so generally through these examples what we observe is that fluid flows, depending on various parameters that are driving the flow, need not remain in a very simple state. Like for example, in the cylindrical jet you have a very nice cylindrical jet, but eventually it breaks up. Okay, so fluid flows can often undergo a transition from a laminar flow to a more complex flow which is turbulent, or to a complex flow state like a bunch of droplets coming out of arising out of this breakup of this liquid cylindrical jet. Okay, now the subject arguably started with the experiments of Osborne Reynolds in Manchester in the year 1883 around. He published a series of papers in 1883, starting in 1883, which reported experiments from that he performed in of flow of water in a glass tube. Okay, this is a cylindrical glass tube. Okay, there is a funnel like entrance to minimize the disturbances into the tube. Okay, and he also used a colored dye stream. This is a colored ink or dye into the flow. Now he observed that when the flow is laminar, right, the dye stream remains parallel. I mean, it just comes out of a like a straight line, assuming that the dye has very low diffusivity, mass diffusivity. So at sufficiently slow velocities, low velocities, the flow is laminar. But beyond a critical threshold velocity, what he found was that the dye, while injecting, initially it remains like a straight line, but then eventually it starts undergoing complicated motion. At still higher velocities, he finds that the dye completely breaks up in the pipe, and the entire liquid of the pipe becomes colored with the dye. The dye is completely mixed up, and the onset of disturbances in the dye's trajectory is an indication of a more complex flow state called the turbulent flow state. Okay, Reynolds himself called this turbulent flow state as a sinuous flow, as opposed to what he called laminar flows as smooth flows. That's the title of the paper. Involves a transition between smooth flow to sinuous flow in a pipe, and then there is a transition between these two flow states. What is also interesting is that Reynolds came up with the notion of dynamical similarity, in that he identified that when regardless of the tube diameter or liquids used, the transition always happens at when the non-dimensional number v diameter by nu. This is the average velocity of the fluid in the pipe. This is the dia, and this is the average velocity of the fluid in the pipe, and this is the kinematic viscosity. When this parameter is greater than around 2000, okay, the flow becomes turbulent. This is the first illustration of the power of dimensional analysis, in the sense that regardless of what diameter you use, what average velocity you use, what density and viscosity of the fluids you use, the transition always happens when this dimensionless group, which we now call the Reynolds number, denoted as Re in honor of Reynolds himself. This is called the Reynolds number. It's a dimensionless number. You should verify this, that it is indeed dimensionless. And whenever Re is greater than 2000, the flow undergoes a transition to turbulent regime in the case of pipe geometry. And this also has macroscopic consequences. When you plot the friction factor as a function of Reynolds number in a log-log plot, okay, in the laminar regime, you know that the friction factor goes as 16 by Re or 64 by Re, depending on the definition. So essentially it goes as 1 over Re. Okay, so the slope will be -1, okay, in a log-log plot. And then there is some transition, and then there is another line, that is the turbulent line. This is laminar, this is turbulent. So there are macroscopic consequences. Remember that the friction factor is nothing but a dimensionless pressure drop, okay, and the Reynolds number is nothing but a dimensionless velocity of the flow. So what you will find is that if I extrapolate the laminar line like this, for a given Reynolds number, the turbulent flow has a larger friction factor or larger pressure drop than the laminar flow, And that can be understood because if you have flow in a pipe, in the laminar flow, all the energy is spent only in pushing the flow in the flow direction, whereas in the turbulent flow, the flow is three-dimensional. While the fluid is on the average flowing in the x direction, there are a lot of fluctuations that tend to push the fluid in the other direction. So all the work that is being done in the fluid is not spent in pushing the fluid in the x direction. So to get the same average velocity, you have to spend more energy in turbulent flow. So turbulent flows have larger dissipation in some sense. Okay, and another important feature about this transition, this is called the pipe flow transition, is that the Reynolds number for this transition RET is typically 2000, but under careful experimental conditions it can be as high as 10 to the 5. Okay, this is something that's very, very important. We'll return to a little later. Okay, so this is what Reynolds found. Now the subject of hydrodynamic stability attempts to understand, which is the objective of this course. The subject of hydrodynamic stability attempts to understand how transition occurs. In the case of Reynolds' experiment, how transition from laminar flow to turbulent flow occurs. And we postulate that the transition occurs due to an instability of the basic flow, basic laminar flow. In the sense that whenever you have an experiment occurring, the experiment is always subjected to disturbances or fluctuations. Okay, experiments subjected to disturbances or fluctuations in the velocity, in the pressure. I will use these interchangeably, or perturbations. Okay, I'll use these three descriptors interchangeably. Now, some of these fluctuations are extremely small or infinitesimal, that they are unavoidable. Okay, so the flow is always subjected to disturbances of various type. That means that in order for you to observe the laminar flow, the flow should be stable to these external perturbations. Okay, so what we attempt to do in hydrodynamic stability is to understand whether a given flow, whether a given laminar flow is stable or not to infinitesimal perturbations, which any flow is subjected to in experiment. We do this in a mathematical or computational manner, but that's the basic idea. You can also understand this very briefly by looking at the following scenarios. Imagine that I have this is gravity. I have a ball in a valley. If I perturb the ball a little bit, okay, then gravity is going to pull this ball down. This is stable. Now if you carefully perch the ball on top of the hill, okay, and if you perturb the ball a little bit, it's either going to go this way or that way. So this is unstable. If you're on a flat portion of land, okay, even if you perturb the ball a little bit here or here, it's going to remain there. It's not going to go away, or it's not going to come back. This is called neutrally stable. So we want to know, by subjecting a flow to small deviations from the laminar state, whether it is going to be remaining in the laminar state or whether it is going to go away from the laminar state. Then we call it unstable. Okay, this is the basic idea of hydrodynamic stability. So I'll stop here for this lecture, and we will